potential of a dipole on axial line is V is equal to 1 by 4 pi epsilon naught, that is P by R square. The same thing, potential of the dipole on equatorial line is zero. Dipole means obviously you'll be having a positive charge and as well as a negative charge like this. Now coming to the another section, that is capacitance. So what is this capacitance? Actually, the capacitor or the capacitance is a device used to store the electrostatic energy. Used to store electrostatic energy. So the charges are the one which will be carrying this particular energy and they can be stored in an static conditions. Movable conditions to store cheyalemu. Okay, that is storage of the charge in store cheyachu ledu ante, or this is a potential energy or it's an electrostatic energy. For an isolated condenser like this, for an isolated conductor which is a charged conductor having a radius r, and a radius undi, then the potential can be written as, and it is 1 by 4 pi epsilon naught into charge by radius, or this I am writing it as an kq by r. From this one, q by v can be written as an r by k, which is a constant, and that constant is called as an capacitance. C is equal to q by v, or from this one, potentially is directly proportional to the charge. So C is called as an capacitance. The general units of the capacitance are farad. Okay, now, so 1 farad is equal to, that is coulomb by potential or volt. So generally, the Earth is a very big conductor. It will have the capacitance ella find out which is a spherical shape. So next, coming to the dimensional formula of the farad is going to be how much? M inverse L power minus 2 T power 4 and amperes square. This is your dimensional formula of this one. Right, Nana? So next in this particular cases, what is the capacitance of an isolated sphere? Isolated charged sphere. So what is the potential of a sphere, and potential of a sphere already we know, that is V is equal to 1 by 4 pi epsilon naught charge q by radius which r. The charge on this one is going to be the q, right, Nana? So substitute this one, C is equal to q by v. Then substituting the v in this case, you will be getting the 4 pi epsilon naught into r. So this is the capacity of a capacitor. It is the capacity of an capacitor conditions. Okay, so any spherical capacitor you can write it. For example, Earth. Earth is a very big capacitor or condenser. So 4 pi epsilon naught into radius of the Earth is 6,400 kilometers into 10 power 3. 1 by 4 pi epsilon naught can be written as a 9 into 10 to the power of 9 into 6,400 into 10 power 3. On solving, you will be getting that 711 microcoulombs. The Earth Earth is a very, very big conductor. So for Earth itself, the capacitance are in the microfarads. Then generally available will be in the microfarads, or it will be micro in the sense 10 to the power of minus 6 farads or nanofarads like this. 10 to the power of minus 9 farads, or picofarads 10 to the power of minus 12 farads. So it will be in these formations. Okay, so please be careful of this one. Now from this one spherical capacitor, we can say that charge C1 by C2 is equal to the R1 by R2, and C is proportional to the charge Q1 by Q2. Okay, so this is the one of the important relationship. So for example, or this is the most important relationship Nana manaku rastunnanu ikkada nenu. It's a very important relationship I am writing. Suppose there are the two conductors over here, two spherical conductors having a charge Q1 and Q2, and radius is R1 and R2. So these and initial capacity C1 and C2 capacitance is not going to change. Initial charges are Q1 and Q2. And now, if these two are connected with an wire, which is a conductor, then charge starts flowing from the one to the other. So in that situation, you can use this relationship also, or else final charges on C1 and C2 are, so final charges on C1 and C2 are, what will be the cases? They are, let it be the Q1 dash and Q2 dash. Then Q1 dash is equal to C1 by C1 plus C2 into total initial charges Q1 plus Q2. Similarly, you can also write for the Q2 conditions or the same relationship in terms of radius R1 by R1 plus R2 into that will be the Q1 plus Q2, right, Nana? This is the situation, please. So you can apply the anything here. So this is another, and the common potential our charges will be flowing till they attain common potential. They attain common potential. What is that common potential relationship? Is V is equal to C1 V1 plus C2 V2 by C1 plus C2, or this can also be written as a total charge will be conserved. So Q1 plus Q2 by C1 plus C2, because since C is equal to Q by V, Q is equal to CV, or V is equal to Q by C also. Or this can also be written as an Q1 dash plus Q2 dash by C1 plus C2. Like this also we can write this one. So this is the common potential formula is very important. Now what is an energy stored in the capacitor while storing this one? Energy stored, or the work done in storing the energy, U is equal to, it is equal to the half CV square, or which can be written as an Q square by 2C, which is also equal to the half Q into V. So these are your different formulas for the energy storage. Okay, na? For the energy storage, these are your different relationships. So in storing a charge kaavachu, or any particular cases or anything like this. Now in the earlier case, the loss of energy in transferring the charge. Just now we have seen one conductor R1, another one is going to be the R2, C1 charge Q1, initial potential V1, C2 charge Q2, potential is V2. These two are connected by the connector. Loss of energy is equal to the half C1 C2 by C1 plus C2 into V1 minus V2 whole square. Loss of energy will be substituting the, that is initial energy minus final energy. You can write that particular thing. Now what is the parallel plate capacitor? Parallel plate capacitor So a parallel plate capacitor is being actually two plates consist of two plates. The shape of the plates need not to be the rectangle. They can be also in an circular plates also. You can apply the electric field because of the positive plate and negative. This is E1 plus E2. Both of them are in the same direction. So resultant E is equal to sigma by 2 epsilon naught because of the positive plate, sigma by 2 epsilon naught of the negative plate. Finally, it is sigma by epsilon naught of this case. Okay, so from this one, we have got, from this one, potential V is equal to E into D. If D is the distance between the plates and A is the area, then substituting in C is equal to Q by V. Charge Q is equal to, you can write it as an potential also, we know this one. So substitute everything here. That is charge by potential is equal to sigma by epsilon naught into D. Sigma can be written as an Q by, that is charge by area into epsilon naught into D. Charge will be cancelled. C is equal to A into epsilon naught by D. Right, Nana? So this is called as your parallel plate capacitor. Fine, Nana, series combination and the parallel combination will be there. So we have seen the formula for the parallel plate capacitor here. Now, what are the other terms of the other formulas of the capacitor here?